Welcome to Limitless Math. Today we're diving into triangle classification, a fundamental concept that will help you master geometry and ace your exams. Understanding how to classify triangles is essential for SAT, ACT, and AP math success. A triangle is a polygon with exactly three sides, three angles, and three vertices. These are the basic building blocks that make triangles unique among geometric shapes. Notice the three sides connecting the vertices and the three angles formed where these sides meet. The most important property of triangles is that the sum of all three interior angles always equals 180 degrees. This is true for every triangle, no matter its shape or size. There are two main ways to classify triangles. First, we can classify them by their sides, looking at whether the sides are equal or different lengths. Second, we can classify them by their angles, examining whether the angles are acute, right, or obtuse. Here's a quick preview of what we'll be learning. The top row shows classification by sides. Equilateral triangles have all equal sides, isosceles have two equal sides, and scalene have all different sides. The bottom row shows classification by angles. Acute triangles have all angles less than 90 degrees, right triangles have exactly one 90-degree angle, and obtuse triangles have one angle greater than 90 degrees. Understanding triangle classification is crucial for your math success. It's the foundation for advanced geometry, essential for trigonometry, and frequently appears on standardized tests like the SAT and ACT. Beyond academics, triangle classification is used in engineering, architecture, and solving real-world problems. In the following sections, we'll dive deep into each classification method with step-by-step examples and practice problems. By the end, you'll be able to identify and classify any triangle with confidence. Let's get started with our detailed exploration. Now we'll explore equilateral triangles, one of the most perfectly symmetrical shapes in geometry. An equilateral triangle has all three sides equal in length, and all three angles measure exactly 60 degrees. Example 1. Here's our first problem. We have triangle ABC with all sides measuring 5 centimeters. We need to identify what type of triangle this is. Step 1. Let's draw triangle ABC and label all the sides. Notice that side AB equals 5 centimeters, side BC equals 5 centimeters, and side CA equals 5 centimeters. Step 2. Since all three sides are equal, this is an equilateral triangle. The key characteristic is that AB equals BC equals CA. We write this using mathematical notation as triangle ABC, where AB equals BC equals CA equals 5 centimeters. Example 2. Now we have an equilateral triangle, where we know one angle is 60 degrees. We need to find the other two angles. Step 1. We know that in any triangle, the sum of all angles equals 180 degrees. In an equilateral triangle, all angles are equal. Step 2. Since all angles in an equilateral triangle are equal, we divide 180 degrees by 3 to get 60 degrees for each angle. Therefore, all three angles are 60 degrees. This is a fundamental property of equilateral triangles. Example 3. Here's a more challenging problem. We have a triangle with a perimeter of 21 centimeters, and all sides are equal. We need to find the length of each side and the area. Step 1. Since all sides are equal, the perimeter equals 3 times the side length. So 21 equals 3s, which gives us s equals 7 centimeters. Now we can draw our equilateral triangle with each side measuring 7 centimeters. Step 2. For the area of an equilateral triangle, we use the formula. Area equals square root of 3 over 4 times side squared. Substituting 7, we get 49 square root of 3 over 4 square centimeters. Example 4. Our final example shows how equilateral triangles appear in real-world architecture. Geodesic domes, like those designed by Buckminster Fuller, use equilateral triangular panels. If each panel has a side length of 2 meters, what's the area of one panel? Using our equilateral triangle area formula, with side length 2 meters, we get square root of 3 square meters, which is approximately 1.73 square meters per panel. Each triangular panel in the geodesic dome has this exact area. The equilateral triangle's perfect symmetry makes it ideal for creating strong, efficient architectural structures. Remember these key properties. Equilateral triangles have all sides equal, all angles equal to 60 degrees, perfect symmetry, and are commonly used in architecture for their structural strength. An isosceles triangle is defined by having exactly two sides of equal length. This creates two equal base angles and gives the triangle a line of symmetry. Understanding isosceles triangles is essential for geometry problem solving and appears frequently on standardized tests. Example 1. Identifying an isosceles triangle. Here we have a triangle with two sides marked as 8 centimeters each. Notice how the equal sides create equal base angles. Step 1. We identify the equal sides. Both AC and BC measure 8 centimeters, making them the equal sides of our isosceles triangle. Step 2. Since we have two equal sides, the base angles are also equal. This is a fundamental property of isosceles triangles that you'll use in many geometry problems. Therefore, this is an isosceles triangle because it has exactly two equal sides and two equal base angles. Example 2. Finding missing angles in an isosceles triangle. We're given that the vertex angle measures 40 degrees, and we need to find the base angles. Step 1. We use the triangle angle sum property. All triangles have angles that sum to 180 degrees. Step 2. Since the base angles are equal in an isosceles triangle, we can call each base angle x. Step 3. Simplify the equation. 40 degrees plus 2x equals 180 degrees. Step 4. Solve for x. Subtract 40 from both sides, then divide by 2. Therefore, each base angle measures 70 degrees. Remember, in isosceles triangles, the base angles are always equal. Example 3, a more challenging problem involving side lengths. We have an isosceles triangle where the perimeter is 20 centimeters and the base is 6 centimeters. Find the length of the equal sides. Step 1, set up the perimeter equation. Perimeter equals the sum of all three sides. Step 2, substitute the known perimeter value and simplify. Step 3, solve for s. Subtract 6 from both sides. Step 4, divide both sides by 2 to find the length of each equal side. Let's verify. 7 plus 7 plus 6 equals 20 centimeters. Our answer is correct. Each equal side measures 7 centimeters. Example 4, real-world application in architecture. A roof truss forms an isosceles triangle with a base of 12 meters. If each of the equal sides makes a 65-degree angle with the base, find the vertex angle. Step 1, apply the triangle angle sum theorem. All angles in a triangle sum to 180 degrees. Step 2, simplify by adding the base angles. Step 3, solve for the vertex angle by subtracting 130 degrees from both sides. The vertex angle of the roof truss is 50 degrees. This creates a stable triangular structure commonly used in architecture. Isosceles triangles provide both strength and symmetry in building design. Key takeaways for isosceles triangles. Two equal sides create two equal base angles. The line of symmetry passes through the vertex angle. These properties are essential for solving geometry problems and understanding architectural applications. Scalene triangles are the most general type of triangle. A scalene triangle has all three sides with different lengths, which means all three angles are also different. Unlike equilateral and isosceles triangles, scalene triangles have no lines of symmetry. Here's our first problem. We have three triangles labeled A, B, and C. We need to identify which one is the scalene triangle. Remember, we're looking for the triangle where all three sides have different lengths. Step 1. Let's examine each triangle's sides carefully. We'll look at triangle A first. Triangle A has all sides that appear equal in length. This makes it an equilateral triangle, not scalene. Now let's examine triangle B. Triangle B has two sides that appear equal in length. This makes it an isosceles triangle, not scalene. Finally, let's examine triangle C. Triangle C has all three sides with different lengths. This makes it our scalene triangle. Notice how each side is clearly a different length from the others. Example 2. Here we have a triangle with side lengths 5, 4, and 6 units. We need to verify that this is indeed a scalene triangle and understand its properties. Step 1. Let's check if all sides are different. We have sides of length 5, 4, and 6 units. Since 5 is not equal to 4, 4 is not equal to 6, and 5 is not equal to 6, all three sides are indeed different. This confirms it's a scalene triangle. Step 2. Since all sides are different, all angles must also be different. Let's add the angle labels. In a scalene triangle, since all sides are different lengths, all angles alpha, beta, and gamma are also different measures. Example 3. This is a more challenging problem. We're given three vertices with coordinates A at 1, 2, B at 5, 1, and C at 3, 4. We need to determine if triangle ABC is scalene. Step 1, we'll calculate each side length using the distance formula. D equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Let's calculate side AB. AB equals the square root of 5 minus 1 squared plus 1 minus 2 squared, which equals the square root of 16 plus 1, or square root of 17. Next, side BC equals the square root of 3 minus 5 squared plus 4 minus 1 squared, which equals the square root of 4 plus 9, or square root of 13. Finally, side AC equals the square root of 3 minus 1 squared plus 4 minus 2 squared, which equals the square root of 4 plus 4, or square root of 8. Step 2. Now we compare the side lengths. Square root of 17 is not equal to square root of 13, which is not equal to square root of 8. Since all three sides have different lengths, triangle ABC is indeed scalene. Example 4. Here's a real-world application. An architect designs a triangular garden with three sides. The north side is 12 meters, the east side is 15 meters, and the south side is 18 meters. What type of triangle is this garden? Let's visualize this triangular garden and analyze its properties. Analyzing the side lengths. 12 meters is not equal to 15 meters, which is not equal to 18 meters. Since all three sides have different lengths, this triangular garden is a scalene triangle. This is the most common type of triangle in architectural designs because it offers the most flexibility in fitting irregular spaces. Let's review the key properties of scalene triangles. All three sides have different lengths, which means all three angles are also different. Scalene triangles have no lines of symmetry and represent the most general form of triangles. Importantly, scalene triangles can be acute, right, or obtuse, depending on their angle measurements. Remember, scalene triangles are the most common type of triangle you'll encounter in real-world applications, from architecture to engineering, because they offer the greatest flexibility in design and construction. Right triangles are one of the most important triangle types in mathematics. A right triangle is defined as having exactly one angle that measures 90 degrees. Example 1. Let's identify the key features of a right triangle. Here's our first problem to solve. Step 1. We draw our triangle and identify the right angle. Notice the small square symbol that marks the 90-degree angle. Step 2. We identify the three sides. The hypotenuse is the longest side, opposite the right angle. The other two sides are called legs. Example 2. Now let's use the Pythagorean theorem to find a missing side length in a right triangle. Here's our problem. We know the two legs are 3 and 4 units long, but we need to find the hypotenuse c. Step 1. We apply the Pythagorean theorem. A squared plus b squared equals c squared. Step 2. We substitute our known values. 3 squared plus 4 squared equals c squared. Step 3. We calculate. 9 plus 16 equals 25, so c squared equals 25, which means c equals 5. The hypotenuse is 5 units long. This is the famous 3, 4, 5 right triangle. Example 3. Let's explore a special type of right triangle called the 45-45-90 triangle, also known as a right isosceles triangle. Step 1. In a 45-45-90 triangle, we have one right angle and two 45-degree angles. This makes it both a right triangle and an isosceles triangle. Step 2. The key property is that both legs are equal in length, and the hypotenuse equals the leg length times the square root of 2. Example 4. Let's see how right triangles are used in real-world construction to ensure structures are perfectly square. A carpenter wants to check if a corner is perfectly square. The method is to measure 3 feet in one direction and 4 feet in the other direction. If the corner is perfectly square, the diagonal distance should be exactly 5 feet, forming a 3 to 4, 5 right triangle. Right triangles are essential in mathematics and real-world applications. They form the foundation for trigonometry and are crucial in construction, engineering, and many other fields. Now we'll explore obtuse triangles, the third type of triangle classification by angles. An obtuse triangle is defined as having one angle that measures greater than 90 degrees. Here's our first example. We have a triangle with angles measuring 110 degrees, 35 degrees, and 35 degrees. Notice that one angle is greater than 90 degrees. The 110-degree angle is our obtuse angle, since it's greater than 90 degrees. This makes this triangle an obtuse triangle. The other two angles are acute angles, each measuring less than 90 degrees. Example 2. Here's a problem where we need to find the third angle. We know two angles measure 40 degrees and 25 degrees. We need to find the third angle and determine if this creates an obtuse triangle. Step 1. We use the angle sum property. The sum of all angles in any triangle equals 180 degrees. Step 2. We set up our equation, 40 degrees plus 25 degrees plus our unknown angle x equals 180 degrees. Step 3. Solving for x, we get 180 minus 40 minus 25, which equals 115 degrees. Since 115 degrees is greater than 90 degrees, this is an obtuse triangle. Example 3 demonstrates a key property of obtuse triangles. The obtuse angle is always opposite the longest side of the triangle. Here we have a triangle with sides measuring 8 centimeters, 5 centimeters, and 4 centimeters. The longest side is 8 centimeters. The obtuse angle, measuring 105 degrees, is located opposite this longest side. This relationship always holds true in obtuse triangles. Example 4 shows a real-world application. In architecture, obtuse triangles appear in roof designs, particularly in modern buildings with unique angular features. This roof section forms an obtuse triangle. The obtuse angle at the base creates an interesting architectural feature while still maintaining structural integrity. Obtuse triangles appear in many real-world contexts. Mountain slopes often form obtuse triangular profiles. Sailboat sails can have obtuse triangular shapes for better wind capture, and some bridge supports use obtuse triangular bracing for structural stability. To summarize obtuse triangles, they have one angle greater than 90 degrees, two acute angles. The obtuse angle is always opposite the longest side, and they're commonly found in architecture and nature. Understanding these properties helps in both mathematical problem solving and recognizing geometric patterns in the real world. Now we'll explore combined classifications, where triangles have both side and angle properties. Here's our first example. Classify this triangle using both criteria. Step 1. Identify the side classification. Notice that two sides are equal. Both legs measure 3 units. This makes it an isosceles triangle. Step 2. Identify the angle classification. One angle measures exactly 90 degrees, making this a right triangle. Therefore, this triangle is classified as a right isosceles triangle. It has both properties simultaneously, 2 equal sides and 1 right angle. Example 2. Here's a more challenging classification. All sides have different lengths, and all angles are less than 90 degrees. Step 1. Check the sides. We have lengths of 4.5, 3.8, and 3.2 units. Since all 3 sides are different, this is a scalene triangle. Step 2. Check the angles. We have 72, 65, and 43 degrees. All angles are less than 90 degrees, making this an acute triangle. This triangle is classified as an acute scalene triangle. Remember, triangles can have multiple classifications that describe different properties. Example 3. This challenging problem requires careful angle calculation. We have an isosceles triangle where we need to determine if it's acute, right, or obtuse. Step 1. Identify the side classification. 2 sides are equal at 5 units each, making this an isosceles triangle. Step 2. Calculate the angles. In an isosceles triangle, the base angles are equal. Using the triangle angle sum property, if the vertex angle is 120 degrees, then each base angle is 30 degrees. Step 3. Since one angle is 120 degrees, which is greater than 90 degrees, this is an obtuse triangle. Therefore, this is an obtuse isosceles triangle. It has 2 equal sides and one angle greater than 90 degrees. Example 4. Real-world application. Architects use triangle classification when designing roof trusses. This triangular support beam needs to be classified for structural calculations. Step 1. Measure the sides. The base is 6 meters, the height is 3 meters, and the hypotenuse is 3√5 meters. All sides are different lengths. Step 2. Check for right angles. The vertical support meets the base at exactly 90 degrees, making this a right triangle. This roof truss is a right scalene triangle. Understanding this classification helps engineers calculate load distribution and structural stability. Triangle classification is a fundamental skill in geometry. Remember these key points for exam success and real-world applications. Practice identifying triangles in your daily life, from building structures to art designs. Master these classifications for success in geometry, trigonometry, and beyond. Thanks for watching Limitless Math. Like this video if it helped you understand triangle classification, and subscribe for more step-by-step math help and exam prep content.